Okay, thank you. And we will continue our exploration of this, and I hope I'm not going to, I hope it becomes a little clearer rather than more confusing. So this is about a way of implementing all that in a very simple approach. So, and I'll talk about this D8-based approach, some applications on that, and a very quick overview of two other implementations. So it turns out there's more than one way of constructing this. Right. So as you may expect, that the full calculation of stream function is actually quite difficult. But there is a very, very simple approach based on essentially the D8 method, which is a very drastic simplification. And the main thing is that it completely ignores dispersal area, which means that the stream function then becomes very tightly linked to contributing area. And the algorithm to compute this is actually only slightly more complicated than normal D8 flow accumulation. So the quick review of D8 contributing area and how that would proceed on a very simple set of cells. We have an outlet cell here, and basically what we need to do is visit each of the contributing cells in turn and add up the areas coming in from each of them. Now with the stream function method, we do exactly the same thing. We're visiting each of the cells in turn, but rather than just adding up the areas, we're keeping track of where we've been and counting partial areas as we go. So just to take you through this, these small numbers along the blue lines in sequence, they are the sequence in which we visit each part of this set of cells. The method, because we're talking about potential flow coming in from up to 7 possible directions, we actually look in each of the directions in turn, and we add 1/8 of the cell area every time we move from one flow direction to another. So the algorithm goes like this. We start off at an outlet cell. We choose a starting value of stream function, 0. And I should comment that the absolute value of stream function means nothing at all. It's all about differences in stream function. So we just choose an arbitrary value to start with. And then we progress very systematically from the outflow direction in an anti-clockwise direction, looking for an inflow from each direction. So the first direction, there is no inflow, so we just add 1. Second direction, we add 1 again, but there is an inflow there. So then we move to the cell above, and we continue going around. So each time we get an 8th cell, we're adding that 8th cell increment. In this case, we get round to the end, and there's no inflowing cells. So at that point, we then assign the stream function value we've got to as the maximum value. When we came in, we assigned the minimum value. So this cell here has stream function values of 2 to 10. Continue with this process, go up through this one. When we come into here, the value's at 11. By the time we come out, it's 19. And again, going up this next cell, it's 20 when you come in. On the way out, it's 28. And when we leave the outlet cell, it's reached 32. So that's the process. And that's just obviously can be extended to any level of complexity of single flow direction network. So I'm going to show you an example with a slightly larger area. Now this is meant to represent a catchment here, all flowing down to an outlet with an internal peak to give it a little bit of interesting complexity. So these are the flow direction arrows, and all these numbers here are the stream function values that are calculated as a result. So you can see the outlet has the largest range of stream function values, and as we progress up the catchments, up the flow lines, the range of values gets smaller as you go up, and they're distinct values as you move around the catchment. So you're looking at the difference in stream function value at every point. Contributing area is simply the difference in maximum minimum value divided by 8 in this case, because we are adding 8 values for every cell we go through. So after you've calculated stream function with this method, you have contributing area for free. So that involves no extra calculations other than a simple subtraction and division. So that's kind of nice. But it's got more applications than that, obviously. So one of them, which has turned out to be quite useful for one of our applications in looking at dam walls around catchment boundaries, is that you can use the algorithm, use the stream function value to trace around the perimeter without having to look at the interior cells. So in this case, we can have an outlet here. All we have to do is scan around looking for an adjacent cell that falls within that stream function range. So moving up to this cell, there's the stream function range there, that's within the outlet range. If we look at the next one up this way, that one's not within the outlet range, so that's not part of the catchment. So we move on to this one, and so on. So you can actually track around the outlet of around the perimeter of the catchment, very, very quickly finding all the cells that belong to the catchment boundary without looking at anything internally and without having to actually follow any flow networks. Another useful feature of this is talking about the significance of features in this flow space. So when we cross a river, we have a major river, we have a large change in stream function, obviously. And the same happens at a catchment divide, and catchment divides often are not particularly topographically distinct. And this is an example of the Great Dividing Range in Australia, not far from Canberra, where, as you can see, the topography is not exactly extreme, but we're crossing over a boundary from flow that goes into the Murray-Darling Basin and flows west compared to part of the landscape that flows east to the Pacific Ocean. So what happens here is that if we look at the stream function values between two adjacent cells, the magnitude of the difference tells us something about how far apart they are in this flow space. So internally in this catchment, we're looking at small differences. Once we get to the edge of the catchment, the difference in stream function value gets quite a lot larger. So that tells us something about how hydrologically different those, or distant those places are. Now here's stream function calculated using the D8 method for Tasmania in the south of Australia. So the colours there, just a colour scale from minimum to maximum. Obviously we've started up in the top left corner here, and some interesting features emerge quite quickly. One of them is this sort of triple point not far from the middle of the island, which is where the major catchments meet. So north of there, water's flowing up there. Just to the east, water's flowing down here in the Derwent catchment, our largest catchment in Tasmania, and to the west of that, water's flowing to the west. And zooming in on an area down here on the Derwent River, we can see there's the topography, you can see the river flowing through the middle there, and that corresponds to a very large change in stream function at along that line. And each of these lines coming in the side is a tributary, and the magnitude of colour change essentially tells you how important that tributary is. We can continue zooming in down to smaller areas, and you see the same pattern all the way down to single cells. So this is capturing this hydrological structure at every scale, from the smallest catchments up to the entire island. Here's a part of the island which is, it's a peninsula, so most of the water's flowing off the sides. So the structure here is dominated by the ridge network rather than the channel network. So that's the D8 implementation and some of the things you can do with it. I just briefly want to talk about two other implementations we have, one of which is called Terre, which is pretty much complete but quite complicated, and there's a simpler method that I haven't yet given a name to. So the Terre method, which is the one that Bruno Basso has supported so strongly over the years, it works by identifying the peaks and sinks and saddles, and calculates contributing and dispersal areas along every cell edge. Now, this is an important point that we're not calculating areas for the cell as a whole, but along each edge of the cell. We construct the divide and the course lines up and down from every saddle, and we actually calculate the stream function discontinuity along each of those. And that's shown in this example here, where we have lines coming up to a peak from various saddles, and each of them has a stream function discontinuity assigned to it. That gives us stream function differences across along each cell edge, and we can then start at some arbitrary point and add the changes in stream function across each cell edge to propagate the values across the entire landscape. This picture on the right shows slope lines. Now these are calculated from the stream function value. So that's calculated, or these slope lines are derived by joining up points on cell edges that have the same stream function value. And it's constructed so that the lines are equally spaced. There's equal change in stream function between them. So the longer flow paths have stream function lines that are narrower or closer together because they have more area that way. The shorter ones are more widely spaced. And the whole point of doing this Terra implementation was to support the construction of flow element networks, which is that component of it is still a bit of a work in progress, but this shows the same piece of landscape I showed in the first talk, divided up into elements conceptually, and here it is done explicitly, that same piece of landscape there represented in stream function elevation space as a set of connected hydrological elements. So there's a simpler method which takes a leaf out of the D8 methods in that it doesn't deal with all the topological complexities directly, but it works around them by forcing them onto cell edges and essentially works around things rather than having to account for them explicitly. I won't go into more detail on that. The key thing that enables that is that going back to this island with a sink, remember that there were the divide lines up from the central saddle have discontinuity of stream function values, and the course lines down to the sink and the other side of the saddle, they're also discontinuous, but there's always a path that you can find from one part of the landscape to another that doesn't cross any line of discontinuity. So that's what enables that other method to work well. Okay, so very quick conclusion. The D8 method is a quick and simple way of calculating the stream function that doesn't give a full representation of it, so it can't be used to create element networks, but it certainly provides enough power to use for a number of useful applications. Thank you.